So we've been looking at circular motion. My good old favorite student. It says this: an airplane turns a complete horizontal circle in 2 minutes. If the plane's speed is 170 meters per second, what's the radius of the circle? Well, they told me is 170, and they told me the period is 120 seconds, 2 minutes, 120 seconds, and they want the radius. I said, well, I know that circular or centripetal speed is 2 pi r over the period. That equation not on your formula sheet, Grant, which is why you're writing it down for some reason. That equation not on your formula sheet. Psst, do you have your stuff here, quiz? Here? Okay. Okay. Oh, they want the radius. I guess the radius is going to be v times t divided by 2 pi. It's going to be 170 times 2 divided by 2 pi. Is that right? I hope. 170 times 2 divided by bracket 2. Where's my pi button? There it is. Pi. Wait a minute. Times 2, Mr. Dueck? It's not 2 minutes. It's times 120, Mr. Dueck. You're looking at the period in the question, but you didn't do the unit conversion. You were doing the math in your head and saying, this seems awfully small. Divided by bracket 2 pi, close bracket. You get 3,250. It's about I made this up. It's about a 3 kilometer radius. This is a plane. It's doing a big horizontal circle. Is that right? 3,250? I'm seeing a few people nodding. I'm seeing a lot of people writing stuff down. Hey, if this is the unit, you're not keeping up with the homework, you're in for the ugly test on the biggest test. Just saying. I would probably give you a half mark for that, half mark for that, half mark for the numbers, and a half mark for the answer. But of course, if you got it right, you're good. What's the centripetal acceleration? Well, I can either go A equals v squared over r, or I can go 4 pi squared r over t squared. In both of them, I'm using the radius that I just found. So Ryan, I'll use the shortest one. I'm going to go 170 squared all over 3,250, but I'm going to use my answer button. 170 squared divided by answer button. And I get 8.9 meters per second squared. Not even a G. One mark for the formula, 1 mark for the number. What's the centripetal force needed to keep an object revolving? Oh, wait a minute. Well, they want the force. That's going to be MAC. Well, there's the mass. There's the radius. Either they gave me the speed or the period. Well, they didn't quite give me either. What they gave me was the frequency, 5 hertz. But understand, the period is 1 over the frequency, or 0.2 seconds. And now I'm good to go. I can say it's going to be m4 pi squared r over t squared, mass times acceleration. It's going to be 12 4 pi squared 6 over 0.2 squared. It's going to be 12 times 4 times pi squared times 6 divided by 0.2 squared is the answer, 71,000 blah, blah, blah. Now, that seems really high, but wait a minute. First of all, let's write down the answer, 71,000 newtons. And at first I thought, that's crazy high, but then I said, hey, wait a minute. What's the mass here? What's the mass here? 12 kilograms, about 25 pounds. You know what? This mass here is almost exactly 12 kilos. So I said, okay, what's the radius here? 6 meters, that's about from me to Sam. And how long is it taking this to go around in a circle? 0.2 seconds. That fast. Okay, if you were spinning a 12, like a hammer throw with a radius of 6 meters, and you're spinning it that fast, oh yeah, that's going to be a huge force. You need a steel cable in the half to do. In fact, a human couldn't do it. You need some kind of machinery. So at first I started to freak out about that answer. Then I looked at the numbers and I went, actually, yeah, it would be a huge force. Like, certainly if it hit you, it would kill you. This is a very fast revolving object with some significant mass. So I stopped freaking out and I went, yay! 3 marks. You know what? I think I actually gave you 1 mark for that, 1 mark for that, and 1 mark for the answer. If you plugged in 5 instead of 0.2, the best you can get is 2 out of 3. But that's, again, if you know the frequency, you know the period. Number 3. Okay, now they want centripetal acceleration, AC. Well, they gave me the speed. V squared over R. 5 squared all over. Is R 25? 0.25. I think I can do this in my head because it's 25 divided by 0.25. Is it subtract 3? 1,000 even? No, that's way off, Mr. Dueck. I'm off by a decimal. 100. 100. Yes? Meters per second squared. By the way, technically, to go to 3 sig figs, I should put a dot there, but whatever. 1 mark. 1 mark. Turn the page. Now, what I didn't put on this quiz for horizontal circles, which I like also, is the car going around a corner where friction is putting it around a corner. Make sure you're comfortable with that. Ferris wheel has a radius of 9 meters. That's about right for a small Ferris wheel. Takes 45 seconds to go around once. That's for a slow Ferris wheel. Person who weighs 65 kilograms, what's the force that the bench exerts? What force are they actually asking me to find? Normal force, and this is at the top. So you know what? Here's my free body diagram. At the top, normal force is pushing up. Gravity down. Why did I draw gravity so much bigger? What path is this person tracing out? So where must the winning net biggest force be? Toward the, and at the top, that's down. So my equation here is going to be gravity minus normal force equals MAC. It's going to be mg minus MAC equals the normal force. So the normal force is going to be mg minus m, they gave me the period, 4 pi squared r over t squared. Going to be smaller than mg, but not by much because the Ferris wheel's pretty tame. 65 times 9.8 minus 65 times 4 pi squared 9 all over 45 squared. Is that right? Do you get 626? No? Yes? 626 newtons. I would probably give you half mark for that, half mark for that, 1 mark for the answer. Same question, but at the bottom. Okay, well, now my free body diagram is going to look like this. What are the forces acting on it? Why did I draw gravity shorter? By the way, I know I drew gravity 2 different arrow lengths. I'm not saying gravity got smaller. This second free body diagram is not to scale. It's just to help me figure out what's bigger, who's winning, whatever's pointing towards the center. In fact, as an equation, it's going to look like this. Normal force minus mg equals ma. Whoop, the c should be down as a subscript, Mr. Dueck. The normal force ends up being mg plus mac. Ready? This is going to be me being real clever. Copy. paste, move it over just a wee bit, and then plus, plus, hey, I'm doing that on purpose, by the way, because 2 lessons from now, you're going to be doing equations that have about 10 different terms, and the first one is a plus, and the second one is you're only changing one of the terms, and I'm going to encourage you, get good at backspacing and just changing your work. It's way less typing, and it cuts down on errors. 648. Thank you. Thank you very much. Okay. Oh, yeah, and the same as before. Half mark. Half mark. You guys notice how I put these little half marky things in? So, pause for a second. 2 stories, but not on YouTube. Usually I tell the car accident story sooner. I forgot. Last one. Suppose we were building a circular space station. Oh, I wish. And we're going to use centripetal force to simulate gravity. Oh, that'd be cool. The station has a radius of 160 meters. All right. We want to simulate a gravitational field. Here's what we really want to do. We want the circular acceleration to be 75% of Earth's. I'll use little g for Earth. We want the circular or centripetal acceleration to be 75% of 9.8. They're asking me for the period, so it's going to be 4 pi squared r over t squared. Mr. Dueck, why didn't you put masses in? I could have solved this with forces, but I said, look, they're talking about acceleration. Why don't I just go straight to acceleration? When we actually solved it in our notes, when we looked at this question, we knew it's the normal force that is the force that's pushing you in a circle, but I just jumped straight to the acceleration. They want the period. I think this is going to move up there, this is going to move down there, and square root. I think the period is going to be 4 pi squared r over 0.75 times 9 times 0.98, Mr. Dueck, times 9.8 square rooted, which is going to be, let's see, 4 pi squared times 160 divided by 75% of 9.8 square root. This would have to rotate almost every 30 seconds, not quite, every 29.3 seconds. Is that right? I think. I'd probably go something like 1 mark if you got that, 1 mark for that, and 1 mark for the answer. Can you give yourself a lovely score out of 3 plus 7, 8, 9, 12, 13, 14, 15. Oh, good, I did get it correct. Sometimes I forget to change the top score when I tweak the quizzes. Give yourself a score of 16, please. As I was entering homework from lesson 3 from vertical circles, for what it's worth, because many of you got this wrong and I didn't include the answer. The answer number 12 is no. You can't ever get dead vertical, no matter how fast you spin it. Let me tell you why. If you could ever get like this, what are the forces acting on that pendulum? Get the obvious one. What else? Well, here's tension, which is what's pulling it in a circle. Why can't you possibly be level? What are the forces down? Gravity. Are there any forces up in that picture? Then Newton's first Emma would kick in. You must accelerate down. What you can do is you can get it nearly level, but never dead horizontal. And when you get it nearly level, you have gravity down, tension this way. And then if you break up this tension, you get, there's the centripetal force. I won't put it on the free body diagram. You get tension X and tension Y, and these two can cancel each other out. It's too bad Ty's not here, otherwise I'd make a joke about him showing up in my free body diagram. So lesson 3, number 8, fighter jet. I don't quite like the way this is phrased because I always wanted to start solving this by doing a free body diagram and I got the wrong answer. I think what I need to do next year is simply add the word net right there. I think this is what they're saying. They're saying whatever the fighter pilot can withstand, it's going to be 8 9.8s. That's the first conclusion. That's a fighter pilot can withstand an acceleration of 8 Gs. Is that okay so far? Which acceleration? Well, it depends. Did they give me a speed or a period? I'll have to convert that to meters per second, divide by 3.6. And so now I can get the minimum safe radius. The radius is going to be, I think these will move down and that'll move up to the top, right? It's going to be v squared over 8 times 9.8. If you divide that by 3.6, I think you get like 830 meters, something like that. Is that okay? Yeah. If you see, to me, I wanted to try drawing a free body diagram and having a normal, and when I do that, I always actually end up with 9 Gs, not 8 Gs. And I think it's because this question gave me the net force, and it didn't say the net force or acceleration. Yeah, me too. I flip-flop every year. Last year I didn't assign this one. 2 years ago I did. I'm sure the year before I didn't. It's a fighter pilots, and it's kind of an interesting question. Oh, okay, how fast can they bank or do a loop at? Fair enough. And I'm sure there's probably, I suspect, because all planes now have computers, there's probably alarms and things that would go off well before you tried turning that sharply. Or there might be a built-in G meter in the plane that starts beeping at you saying, look, you're approaching what your physical body can handle. Don't do that. Yeah?
Question 2 on this.
On this one as well?
Yep.
Question 2? E and F? So, we're mass on the end of a string. Force diagram, definitely gravity down. Tension towards the middle. Why did I draw tension bigger? Right? So the equation is going to be was that it? And I'm hoping they gave they gave me the speed, so I'll use the mv squared over r. And this is why I said, I can't remember if you were here, where is a rope most likely to break? At the bottom, right at the bottom of the swing. Hey, Google in YouTube fail rope swings, and I'm sure you'll see some where they break, and it's always right at the bottom. Any others? Yeah. Number 9. I like this question. This is a horizontal circle, which is why I stuck it on there. It was a good review. Hey, what are the forces acting on that car? Yes? Is it sinking into the ground? What path is it tracing out? What force am I putting there? Don't say FC. That doesn't appear on the free body diagram. Friction. So, friction equals MAC. That's the winner. Mu times the normal force equals, and I saw they gave me a speed, so I'm going to use v squared over r. You caught it was kilometers per hour, so you divided this by 3.6. Yeah. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Apparently cars and trucks can drive on the same roads, kind of convenient. So I think it's going to be mu equals v squared over, we've seen this GR expression show up occasionally, should be that. Okay? Any others? Any from the gravitation lesson? So I'll still take questions, but as far, oh, I'm sorry, Luna. Could you slouch a little more and get a little smaller? Number 10 on this one or the next one? On the gravitation?
Yeah.
What was number 10? I don't remember. I don't think Sure. Sure, this totally works. Orbits. Hey, rocket science. Here's a picture of mass little m. Let's pretend it's a satellite. And it's in orbit around a planet, big M. Draw the force diagram for the mass. What are the forces acting on this object? Oh, I can say get the obvious one, but please be very careful. Which way is gravity? Are there any other forces in outer space acting on it? There's no friction out there. So, gravity. Who's winning? In fact, here's the equation that we're going to be flogging to death for the next couple of lessons. Gravity is what's pulling me in a circle. Are we on the surface of the Earth? So can I, this is wrong, can I go like this? Which version of gravity must I use? Big G, big M, little m over r squared equals, and it's either going to equal mv squared over r if they tell me the orbital speed, or, guys with me? Big G, big M, little m over r squared. It could be m4 pi squared r over t squared if they tell me how long it takes for it to get around the planet, if you tell me the period. And you may notice there's some stuff that can cancel, and we'll tackle all that. But for now, if I'm in orbit, gravity is what's causing the circle. So, an orbit is circular motion with gravity as your inwards or centripetal force. Example 2, a 10,000 kilogram satellite is orbiting 20,000 kilometers above the Earth's surface. Can all of you underline above the Earth's surface, please, and the 20,000 kilometers? First thing it says for part A is write force equations. Logan, if it tells you you're in orbit and it starts talking about force, you can say gravity is pulling me in a circle. There's my answer to A. Now I'm going to break those equations down. What's B asking me to find, Jake? Speed or period? Speed. I'll use the centripetal one that has the speed in it. I can now say for part B, oh, I guess it looks like big G, big M, little m over r squared equals mv squared over r. Oh, I noticed something. What? A tiny satellite will orbit at the same speed as the space station. The masses up there cancel. Actually, I noticed one more thing. How many r? One of the r's will cancel because this r could end up on the top, and you'd have one r on the top, one r on the bottom. One of the r's cancels, but not both of the r's. The squared on the left and the r on the right. And in fact, what did you say we're trying to find? Oh, you know what? We end up with this. V orbital speed, is equal to big G, big M over R. Actually, Jake, that's V squared that we got. Oh, how do I get rid of a squared? Big G, not 9.8, yet what? The universal constant of gravity. Big M is the mass of the thing we're orbiting. What are we orbiting? Hey, conveniently, that mass is on my formula sheet. Yes, Vanessa already went and looked. Good. 5.98 times 10 to the 24th over. Now, R is the distance from the center of the planet to the satellite. What phrase did I tell you to underline? Guys, have your attention span back here? I know someone dropped some money, but focus is important. What phrase did I tell you to underline? Above. So this distance here is 20,000 kilometers. Let's convert that to meters. Can somebody multiply that by 1,000 and then give it to me in scientific notation? Can you possibly be dropping and distracting more? Okay, we're back. Can someone go 20,000 times 1,000, and then what is that in scientific notation? I'll give you a hint. It's 2 times 10 to the 7th or 8th? Okay, so this is 2 times 10 to the 7th, but that's the distance above the Earth. Where do we measure from? Center of the Earth. How can I find the orbital radius? Add what? Okay, so in the bottom here, I'm going to have my altitude added to, what's the radius of the Earth? Oh, hey, that's on my formula sheet too.
I got you.
I'm glad you do.
6.38 times 10.
I'm comforted by the fact that you got my back. It's well worth practicing typing these in. Do the square root last. Type the top, divided by, type the bottom, and yeah, you'll have to put brackets around the bottom because there's a plus sign. Hit enter, and then square root. By the way, some of your scientific calculators might have big G programmed in. You might have a key that actually is the gravitational constant. It's less typing if you have it. Use it. If you're not sure, it might say in the inside cover of your case. Orbital speeds are usually in the thousands of meters per second or in the tens of thousands of meters per second. So there you go. 3,890. I like that question. I like that question. I like that question. And again, notice that the little m's canceled. Orbital speed is independent of the mass of the orbiting object. It depends only on orbit speed and radius of the central mass. I'm going to write the equation that we derived here, the fact that V orb equals big square root of big G, big M over R. This is not on your formula sheet, but my starting point, my trigger word, Logan, if they say the word orbit and they start talking about speeds or periods, and then I derive it. And then I derive it. That's how fast you need to be traveling to stay in orbit. If you're traveling slower, you're going to fall down towards the Earth. If you're traveling faster, you're going to arc off and shoot into outer space. Both of which would be bad. We really haven't talked about what an orbit is, though. Example 3 says, fill in the proof below to show that when an object is in orbit, its inwards acceleration is the same as the gravity field at that distance. In other words, prove that objects that are in orbit, Halen, are actually falling. Every satellite is falling to the Earth. The space station is falling to the Earth. Really? Well, why aren't we getting... We'll talk about why we're not getting hit by them, but they are, and here's the proof. A equals... What's our equation for inwards acceleration? V squared over R. Then it says substitute V equals for orbit speed. What did we just say was the orbit speed? Why, square root of big G, big M over R. By the way, that's V. What would V squared be? What would vanish? The square root. Okay, so I have this then. A equals big G, big M over R, and then times 1 over, there's the R from here. So I drop that down. How many R's are really on the bottom? you know what, scribble this out and just put a squared there. And last unit, I told you that big G, big M over R squared was gravitational field strength when we went away from the Earth. What we've just done is we've proved, McKinley, anything floating in space is not. Sorry. Anything floating in orbit is not floating. It's falling. So why don't they hit us? Well, Sir Isaac Newton, when he first derived his law of gravity, of universal gravitation, he imagined standing on the top of a very, very large mountain and firing cannons. You could fire a cannon little ways and it would hit the ground. If you had a really, really strong cannon, it might curve partway around the Earth before hitting the ground. He said, you know what, it seems to me that there is some velocity, if I fired it just right, where it's still technically falling, but its horizontal component is exactly big enough so that it's matching the curvature of the Earth. That's an orbit. Objects in orbit, none of them, Logan, are floating up there. They're all falling. But what we do is we give them just the right orbital speed so that as they fall, they also move sideways, and the Earth literally curves away from them at the exact rate as they are falling back towards the Earth. Which means, Emma, astronauts are not no gravity. They're in apparent weightlessness. In fact, I felt exactly the same thing that the astronauts do when I jumped out of an airplane. I mentioned I jumped out of an airplane, except I felt the wind on my face, so I knew I was falling. They're in an enclosed room. The only way they know that they're falling is, oh, they're weightless. Not massless, weightless. There's no normal force. What this means is that objects in free fall are always falling towards the Earth, even if they never get any closer. It explains why astronauts seem to float in the space shuttle. Both the passengers and the ships are in free fall, and so it's not that mg is zero, the normal force is zero. This is why I've gone on that rant for years about what you guys think of as your weight is actually the normal force. Take that away, and you would think you were floating. And it means that astronauts experience continuously, until they get used to it, the physiological feeling of falling. In fact, the astronauts train in a jet. The jet dives down to the Earth 30 seconds at a time at negative 9.8 meters per second squared. So they're in free fall, and they get to experience brief bouts of 30-second weightlessness. Do you guys know the nickname for the jet? It's called the Vomit Comet. Okay? And it's called that for obvious reasons. At the same time, I don't think any of you would say no to going on it. Even if you knew that meant you're going to be upchucking a few times, I would still totally go on it. Of course I would. Example 4, turn the page. In a cartoon, a character kicks the football the wrong way, but the football orbits the Earth and still goes through the uprights from the other way around. Okay, at what speed would that football be moving? What are they asking me to find here? This football is in orbit. They've talked about speed. I'm going to write down gravity is what's pulling this thing in a circle. Where gravity is going to be big G, big M, little m over r squared. And it's going to be m period or speed, because they want speed, v squared over r. Did they tell me the mass of the football? Did they need to? That's why they didn't tell me. Oh, and one of these r's will cancel. In fact, I could have gone straight to v orb equals big G, big M over R. But I derive it because it's a fairly cool derivation, and I'll memorize stuff that's tough to derive. Okay. Let's plug in numbers here. What's big G? Oh yeah, 6.67 times 10 to the negative 11. There's the constant of gravity. Mass of the Earth, 5.98 times 10 to the 24th. Are we on the Earth's surface for this particular example? Then you know what? The radius of the Earth, I mean, yeah, you're technically like 3 meters or 4 meters higher. That's not really going to make a difference. What is the radius of the Earth?
6.38 times.
Remove the football. Suppose you wanted to build a rocket ship that would orbit the Earth just above the surface of the Earth. Maybe 1,000 feet up so you'd clear any skyscrapers. Well, actually, nowadays, 3,000 feet up so you'll clear any skyscrapers. There's some mountains, but you could find a path where there were no mountains. How fast would you have to travel? What did you get, Vanessa? 7,000. 7,907? I know it's just shy of 8 kilometers a second. Before we answer B, let's talk about C. Why isn't it actually possible to orbit the Earth's surface in this manner, although it would be very possible on the moon? Air resistance. Your rocket ship would heat up, and the air resistance would slow it down. You could not shut your engines off and orbit. You'd have to continually be adding energy. Okay. Hey, Ryan, what's B want me to find? Period. Are we in orbit?
Yes.
Oh, well then I'm going to start out by writing Fg, gravity, is what's pulling me in a circle. I'm going to write down big G, big M, little m over R squared equals M. Am I going to write V squared over R? I'm 4 pi squared R over T squared. Did they tell me the mass of the football? Nope. Does an R cancel this time? And this is one of the common mistakes. Wouldn't this R actually move down and actually give me an R cubed down there? So the R does not cancel this time. What did you say we're trying to find? Let's get this by itself. I think, Ryan, this would move up to here. These would move down there. And this R squared would become an R cubed up there. Is that okay, Rach? Can we do this? By the way, in Physics 11, when I started teaching my students that stuff moves diagonally, it was specifically for these two equations. The FC, the velocity and the speed one, because it's so nice if you can derive it in one step. It saves you huge amounts of writing. So I get this. T squared equals, okay, there's going to be a 4, a pi squared, an R cubed. And on the bottom, there's going to be a big G, a big M. Now that's T squared. Help me out. That's T squared. And now it's plug and chug. You all want to practice typing this one in. I need more room. The period is going to be, how long would it take you to go around the Earth at 8 kilometers a second? Approximately 8 kilometers a second. 4 pi squared, 6.38 times 10 to the 6th cubed, all over 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th, Four pi squared times 6.38. I can't imagine you making a sloppy mistake, Carly. Divided by, when does that ever happen? 6.67. Oh. times 5.98. First, let's see if I type this right. 4 pi squared r cubed. I'm not sure if I need to put it in brackets or not. I'm going to try it without, and I'll find out on my calculator how my calculator works. And then I square root, and I get 5,070 seconds. Or, divide by 60, every 84 minutes, you'd go around the Earth in a little under an hour and a half. Putting that in perspective, the ISS, the International Space Station, orbits the Earth every 96 minutes. Or 94 minutes. I think it's 96 minutes. We can calculate it. Yeah, we can, actually, but not right now. What did we say the answer to C was? If we ever do build colonies on the moon, though, I'm telling you, it would be very, very simple and convenient to have a bunch of the satellites on the moon orbiting maybe 3 kilometers above the surface as opposed to several hundred kilometers above the surface the way we do now. They'd go zipping past, you'd get used to it, but sure. Is that a question or you're... Good. Suppose, oh, next one, example 5. Suppose you're building a communication satellite, sorry. Suppose you're building a spy satellite and you want to go around the Earth every 300 minutes. Where do we put it? How high does it need to be? Yep.
I don't know how to get cubed and
You're looking for this button right here. That's to the power of.
and it said, oh, never mind. Thank you.
Okay. So the U.S. military, oh heck, many countries that have spy satellites would say, oh, we want to be able to cover the Earth with this satellite every 300 minutes. We'll convert that to seconds. 300 minutes, by the way, is what? Every 5 hours. Okay. How high did the space shuttle need to put it up there? Or if they use a rocket to put it up there, how high does the rocket need to go? Are we in orbit? Have they asked for or mentioned period or velocity? Then we start out by saying,
Gravity is what's pulling me in a circle.
I hope, Sam, you're noticing a common theme here. What I'm really saying is this. If I tell you the orbital radius, or the speed, or the period, I can ask you to find any of the others. Big G, big M, little m over r squared equals m 4 pi squared r over t squared. Hey, a mass cancels. Does an r cancel this time? No. What are they asking me to find here? Which is what in this equation? Okay. I went to go see a pirate movie the other day, but I couldn't get in. Why? Because it was rated R. Okay. They're asking me to find R. Right? Really? I haven't used that joke yet? I usually use it sometime in this unit. So I think this is going to move to there. This is going to move up there. And the 4 pi squared is going to move below. And we're going to get this. Big G, big M, t squared over 4 pi squared equals r what? Oh. All right. How do I get rid of a cubed? Cube root. Holy smokes, Mr. Dueck. You mean there is actually somewhere where higher order roots are useful? Yeah. We show them to you in grade 10, but we never actually say, oh, you know what? Actually, turns out cube root is used. So how do I write that? Cube root. And now it's going to be your job to find your cube root button in just a second. Let's first of all fill in the numbers because we have to make some adjustments here. Let's see. R is going to be the cube root of 6.67 times 10 to the negative 11, 5.98 times 10 to the 24th. Folks, they said 300 minutes. How do I convert minutes to seconds? Can I just go 300 times 60 right in the brackets? Because I'm going to do it anyways. Why not just do it there on the fly? Divided by 4 pi squared. Now I'm going to pause and walk around if you need to find your cube root button. Do the same as the square root trick, though. Type everything, hit equals, and then cube root answer. I think works much better. Carly forgot to put a squared on this, so we'll put a squared right there. Yeah, that's on YouTube now. So our orb, the orbital radius, the height, no, sorry, the distance from the center of the Earth is, can someone read it to me? It's 1,4,848. 0.9. Can I go 6 and just stop there? Okay. Now that's the orbital radius. What that has done, if this is the Earth, we have found this distance. We would like to find the height. How can we find the height? Subtract which radius? Okay. So final step is going to be height equals our orb minus our Earth. And you all have this number still stored on your calculator, so you can just go minus 6.38 times 10 to the 6th. I haven't typed any of these in, so I'm not going to do, well, I guess I can type that in. 14848,096 minus 6.38 times 10 to the 6th. And that satellite would have to orbit 8.47 times 10 to the 1, 2, 3, 4, 5, 6. That many meters above the Earth, or if you wanted to, divide by 1,000. It's orbiting at about 8,500 kilometers above the Earth, just shy. Okay, and yeah, we have stuff that's that high up. What's its orbital velocity? Justice, now you may. What's its orbital velocity? Oh, are we in orbit? Is it asking for speed or velocity or period? Well, then heck. Oh, you know what? Since we just did it, it's still in my brain. But I can always derive it if I forget. Which R am I going to use? The height? The 8.47 times 10 to the 6th? Or the orbital radius from the center of the Earth? Make sure you use the orbital radius from the center of the Earth. And you're going to, Maris, have to read the questions carefully, because sometimes I'll just ask you to find the orbital radius, and sometimes I'll say, tell me the altitude, which means, okay, subtract the radius of the planet. Sometimes I'll give you the altitude, which means add the radius of the planet if you're going to turn it into a radius. Or sometimes I'll give you the orbital radius. Just read the question carefully. In this one, it's going to be 6.67 times 10 to the negative 11. 5.98 times 10 to the 24th. All over 148,48096. 148,48096. Do you get an orbital speed of about 5,183? No?
Yeah.
Yeah? 5,183 meters per second? So is this thing moving?
Yeah.
Yeah? Fairly fast? So does it possess kinetic energy?
Yeah.
Where does that energy come from? This is why it's so expensive to put stuff up there. This is why you'll see huge rocket with a tiny payload. Where is that energy coming from? All the fuel in the rocket. There's just no way around it. We have no way of figuring out how to get stuff using rockets in orbit for cheaply. Because not only do you have to give it potential energy of 8,000 kilometers above the Earth's surface, which takes fuel, then you've got to give it sideways speed of 5,000 meters, 5 kilometers per second, which takes fuel. So if we want the equation that relates period and orbit, we said it was Fg equals Fc, big G, big M, little m over r squared equals m4 pi squared r over t squared. I think I'm going from memory and trying to rederive it in my head, but it was 4 pi squared r cubed over big G, big M. Is that right? I think, yeah. The r squared moves to the top, gives me an r cubed. The t squared goes up to the top on the left by itself. The big G, big M, yeah. Oh, square root. Okay. The one that I don't think I'm going to put in a box is getting the r by itself, but that's, hey, cube root! Kind of cool. Only cube root if they give you the period. So it was square root, I think. No, I think nothing if you gave you the speed. How much more do I have to get that? One more. Good. A satellite has an orbital altitude of that. I underlined altitude. I think I'll have to add the radius of the... oh, no, it wants me to find its orbital radius. We're going to assume we're around the Earth here, because I forgot to say that in the question. Whoops. We're going to find its orbital velocity. And then for some strange reason, I have part B twice. So we'll call that part C, because that's how most of the alphabet rolls. What's its orbital period? Okay. I like this question. I like this question. I like this question. What's its orbital radius? Well, the orbital radius is going to be what? Altitude plus the Earth's radius. So it's going to be 1.2 times 10 to the 6th plus 6.38 times 10 to the 6th. You don't need a calculator. They're both times 10 to the 6th. So it's really going to be 1.2 plus 6.38. I think 7.58 times 10 to the 6th. You can check me if you want, but I'm pretty sure I'm right. Is that okay so far? Good. Do B and C on your own. I'll do them up here. Let's see if we get to the same spot. Always from the center of the planet. You getting the 7,000s for the orbital speed? Seems right. 6, 5, 7. Yeah, every 109 minutes is about right. That's what I got. There is actually a shorter way to get there. Once you've done part B, once you know the speed, you could go like this. Well, it's moving in a circle, and that has to be the same as if it's... You could go straight to solving for t like that, because it turns out this v is big G, big... It actually, if you plug it into that also works. It's up to you. Rocket science. What's your homework? Number 1. Number 2. 3 is good. 4 is good. 6 is good. 7. A geosynchronous orbit, which actually we have lots of satellites in geosynchronous orbit, is one where the satellite appears to stay above the same point at all times. For it to do that, what must its period be? Ashley, 24 hours times 60 minutes times 60. They all have to have the same period, which I think means they all have to have the same height and same orbital speed. So try number 7. 9. 10. I'll pause there. Good.